Okay. Okay, well, everybody, let's just take a look at Unit D2, boundary layer and viscous effects. Okay, so this unit, we're going to take a look at all about boundary layer theory, which is essentially a flat plate boundary layer. Flat plate means there's no pressure gradient. Okay, so we are going to take a look at what is the boundary layer, then laminar versus turbulent flow, and then we are going to try to solve boundary layer thickness and then skin friction coefficient for the flat plate in the case of laminar and turbulent boundary layer. And then we are going to try to understand what is really happening in airplane, trying to explain from the viewpoint of what is the boundary layer, and then this is all about viscous effects of airplane. So let's just take a look at page 1. So let's begin with what is boundary layer. Boundary layer is usually very, very thin layer right next to the surface of a vehicle. If this is airflow, this is going to be very, very thin. Now, within this thin layer, because of the viscosity, the velocity changes from, this is a free stream, to 0, usually non-linear. This is called boundary layer velocity profile. Now, if you take a look at velocity profile, based on the Newtonian fluid equation, viscosity times dV dy becomes tau wall. This is the shear stress. Shear stress is maximum right next to the wall. So this is called wall shear stress. So let's just take a look at it. This is called wall shear stress. TW. This is a shear at the surface, something called wall surface. This is the viscosity times dV dy. This dV dy is the change of velocity in the direction perpendicular surface from the surface. This becomes maximum. So if you measure dV dy at the location y equal to 0, this is going to be a maximum value. So this tau wall is usually the maximum shear stress developed on the wall. So this wall shear stress essentially produces the skin friction drag. This is the type of drag that you need to compute if you include the viscous effects in aerodynamics. Okay. Boundary layer usually starts from the leading edge of the surface, in this case flat plate. Now, the thickness of the boundary layer begins to grow as you move toward the trailing edge. This thickness is called delta, called boundary layer thickness. We can compute this delta in terms of Reynolds number. We are going to take a look at later. Okay. So, Reynolds number, obviously, this is Reynolds number. Reynolds number based on x. X is the horizontal distance measured from leading edge is called x. So Reynolds number based on the x, this is going to be very important condition for boundary layer growth, as well as the value of shear stress, or in turn value of skin friction drag. Let's take a look at the next page. We need to take a look at two different kinds of flows. One is a laminar flow, one is turbulent flow. Now, flow usually begins as a laminar. Okay. Now, this laminar flow begins to transition to turbulent flow. Turbulent flow is more chaotic, random motion. And then, if you look at boundary layer on the flat plate. Okay. So boundary layer begin to develop. At the beginning, this is usually laminar. Then this laminar flow begin to transition into turbulent flow. oftentimes we need to define the transition point, XTR. So this is called transition from laminar to turbulent. Okay. This transition point is usually defined by what is the Reynolds number that actually causes the transition. So if you know the Reynolds number for transition, you can sort of predict the point of transition, next transition here. Okay, so this is the laminar flow region. So if you take a look at velocity profile, it's going to be like this. This is a turbulent flow. So this is sort of like velocity profile. So velocity profile between laminar and turbulent will be different. Let's take a look at those two differences. So this plot, laminar flow, this is the usually the laminar flow velocity profile. This is the turbulent flow velocity profile. As you can see, over a small tiny distance dy, the velocity originally 0 to velocity over dy, dv dy is larger for turbulent flow than laminar flow. Okay. Because of the velocity profile will be different. So because of that, if you compare the wall shear stress from the case of laminar wall shear stress in the case of turbulent. So this is way larger, right? Because simply because dv dy at y equal to 0, dv dy at y equal to 0, this is much larger value. Okay. So let's move on to the next page. So now in this unit, unit D2, of course you are going to run viscous fluid flow in aerodynamics too. So Ae301, this is just introduction. So we are going to take a look at simplest possible case, which is flat plate. Flat plate means that there is no pressure gradient, so the pressure doesn't change over the surface. Without the pressure gradient, we can fairly easily define. This is the thickness of boundary layer. This is the skin friction coefficient. This is in terms of Reynolds number both. And because of that, you can define CFX. This is called skin friction coefficient. This is a function of course, wall shear stress. And then this is the skin friction coefficient at the location X. So let's use this. This is called Brescia's solution. It's a flat plate boundary layer solution. We can use this one to compute simple examples of flat plate boundary layer. So let's take a look at the laminar case. Next page. Okay. So let's consider a flow of air over a flat plate. So this is a flat plate. So let's see, very thin flat plate. Okay. Length is 5 centimeter. Width is, let's say, unit width. So let's say this is 1 meter. Okay. This is all uniform flow. It's not uniform. It's like laminar. Laminar uniform flow. Okay. The free stream condition corresponds to standard sea level. And the flow velocity is V infinity is 120 meters per second. Okay. Determine the following. A. Boundary layer thickness delta at the trailing edge of the plate. B. The drag force due to skin friction developed on the plate. Okay. So let's begin with A. The boundary layer thickness delta at the trailing edge. At the trailing edge, where x is equal to 5 centimeter, Let's determine Reynolds number. Reynolds number as a function of x. So this is rho infinity v infinity x divided by mu infinity. So in this case, note. Sorry about that. Note. Rho infinity. This is a standard suitable body. Let's pick it up. 1.225 kilogram per cubic meters. Velocity. This is given 120 meter per second. Free stream. X is 0.05 meter. Viscosity at the standard sea level is 1.789 times 10 to the minus 5 kilogram meter second. Okay? So these are standard sea level, standard sea level. This is given velocity, this is x. So let's just plug in those values here. Density is 1.225 kilogram cubic meter times velocity 120 meter per second. X is 0.05 meter. Viscosity 1.789 times 10 to the minus 5 kilogram per meter sec. Reynolds number is 4.11 times 10 to 5. So this is a Reynolds number at the trailing edge. Okay. So at the trailing edge, you can determine boundary layer thickness. Let's use the equation given in the previous page. Laminar case, delta is equal to 5.2x divided by square root Reynolds number. So this is 5.2 times 0.05 meter divided by square root 4.11 times 10 to 5. 4.06 times 10 to the minus 4 meter. That means this is 0.0406 centimeter. So this is the boundary layer thickness at the trailing edge of 5 centimeter plate. 0.0406, very, very thin layer, of course. B. Okay. So let's determine the drag force due to skin friction. Total skin friction. In terms of coefficients. Let's use the equation from previous page. CF, skin friction coefficient, is 1.328 divided by square root Reynolds number L. Now REL is a Reynolds number at x equal to L, at the trailing edge usually. Okay, so as a result, total skin friction coefficient 1.328 divided by square root 4.11 times 10 to 5, 2.07 times 10 to the minus 3. So this is the total skin friction coefficient developed on the plate. Now, how much skin friction drag is developed? Let's find out dynamic pressure of the free stream. This is 1/2 rho v squared. This is 0.5 times density 1.225 times velocity 120 meter per second squared. Can you see it? Okay. This is going to be 8,820 Newton per meter squared. So this is dynamic pressure of free stream. Area S This is something called projected plane form. Let's remember the definition of projected plane form from unit A5. So this is 0.05 meter times 1 meter. So this is 0.05 meter squared. Therefore, skin friction drag is Q infinity SCF 820 0.05 meters squared times 2.07 times 10 to the minus 3. Drag is 0.913 Newton. Now this is not the answer here. One thing we have to be very careful about was this drag force is developed on one surface. Now this is a flat plate placed in a free stream. So you have 1 and 2, top and bottom 2 surfaces. So dF total is 2 times dF. The reason is both top and bottom surfaces. Therefore, total value is 1.826 newtons. So this is the answer. So this is a single surface. You have this much skin friction drag. For both surfaces, this is total skin friction drag. Skin friction drag is oftentimes called parasite drag. Parasite drag means every single exposed surface on your vehicle's body, that area needs to be considered. That means this one has 2 exposed surface, one surface and bottom is the second surface. So total skin friction drag is this surface and bottom surface both. Okay, let's be careful about that. All right. Next page. Next page is essentially very similar solution called turbulent boundary layer solution. Okay. So turbulent boundary layer, it's a little bit different from laminar case. So this is the skin friction coefficient if the flow is turbulent. Again, this is the function Reynolds number. This delta is also function Reynolds number, but it's going to be a different function Reynolds number. Okay. Now, of course, turbulent boundary layer is as a result of transition from laminar. And then usually this is going to be much thicker than the laminar boundary layer. Okay. Now transition, what causes transition is still lots of things involved in order to have a transition from laminar to turbulent. But one can actually do forced transition from laminar to turbulent by putting maybe strip wire or maybe dimple, some kind of surface roughness. Those kind of things actually force transition from laminar to turbulent. Okay. But those are really beyond our scope of this unit A2. So let's just take a look at the next page. Let's repeat the similar example. Okay. So this is the case of turbulent boundary layer. So let's consider a flow of air over the same flat plate. The free stream condition corresponds to standard sea level and the flow velocity is 120 at the same time. If the flow is turbulent, what is the boundary layer thickness? And what is the drag force? Let's just repeat the same computation in case of turbulent flow. Okay, so let's start with A. Reynolds number is the same thing. Reynolds number at location X is rho Bx mu infinity 4.11 times 10 to the fifth. Same Reynolds number at x equal to L, which is 0.05 meter. So, boundary layer thickness, let's use the equation for turbulent flow, which is the previous page. 0.37x divided by Reynolds number to the power of 0.2. 0.37 times 0.05 meter divided by 4.11 times 10 to the 5 to the power of 0.2. So this is 1.39 times 10 to minus 3 meter, which is 0.139 centimeter. Okay. So this is much thicker than the laminar case. This is actually 3.42 times thicker. Now laminar boundary layer. Okay. So what about the total skin friction drag coefficient? CF is 0.074 divided by Reynolds number L 0.2. 0.074 divided by 4.11 times 10 to 5 to the power of 0.2, which is equal to 0.00558. So the same thing happens. dF is equal to Q infinity SCF. So this is 1/2 rho V square. Area is 0.05 meter square. Skin friction coefficient 0.00558. Skin friction drag is 2.46 Newton. Total DF 2 times DF, which is 2 times 2.46 Newton, which is 4.92 newtons. This is 2.7 times larger by laminar boundary layer. Okay. So as a result, if you take a look at it, for the case of turbulent boundary layer, the boundary layer thickness tends to be much thicker than laminar flow, and then skin friction coefficient is much larger than laminar flow. Okay. All right. So next page. So now we looked at flat plate laminar and turbulent boundary layer computations. So we want to do some a little bit more practical computation. Suppose if you have a transition happens. So let's take a look at the airplane. In this case, this is a biplane. Now, on one of the surfaces, let's assume that the wing is made up by a flat plate. Okay. One of the wing surface, this happens. Starting from at the leading edge, you have a laminar boundary layer developed. Now somewhere in the middle, location called XTR, this is a transition. So right at this point, flow transition from laminar to turbulent, then become a laminar boundary layer. If you take a look at from the side, this is the picture here. Okay. So right here at the trailing edge to the transition point, flow is laminar and then become turbulent. If this is the case, what is the skin friction drag coefficient? Can we compute such a thing? Let's just take a look at this one. So the wingspan of Wright Flyer 1 biplane is, this is the wingspan B. Wingspan is 40 feet 4 inches. Okay. And the platform area, this is the platform area of each wing is 255 feet square. that actually gives you what's the coordinates. So platform area divided by wingspan gives you coordinate C. Okay. Assume that the wing is a rectangular shape. If the airplane is in flight with 30 miles per hour under the standard suitable flight condition, let's estimate the skin friction drag on the wings. Assume that the transitional Reynolds number is 6.5 times 10 to 5. So this is a Reynolds transition. So this is the knowledge that we have under this Reynolds number, flow transition from laminar to turbulent that actually determine this X transition. Okay. So I'm not going to actually solve this problem right here. This is actually one of the homework assignments. So I'm going to tell you the procedure of this analysis here. So step number 1. Let's calculate skin friction drag force dF. Let's call this dF A plus B. Assuming that flow is turbulent. This is step 1. So what I'm going to do is, this is one of the wings. Suppose if this is all turbulent flow. Let's compute dFAB. Let's call this dFAB turbulent. So this is step 1. Step number 2. Obtain dFB turbulent. By subtracting dF A plus B turbulent minus dF A turbulent. So that means this. So now you are going to compute, this is a transition point. So this actually gets you dF of A turbulent. So whatever the value you obtained here, if you subtract this one from here, what you end up having is this. This is the transition point. This is the dF of B turbulent. So you are going to isolate area B, which is, let's go back here. You're going to isolate skin friction drag generated at the area B because we know this is turbulent flow. Okay? Let's go back here. So in order to obtain that, you need to compute the A plus B area. If its flow is turbulent, what is the skin friction drag? dF A plus B. Subtract area A only for the turbulent flow. Then ended up being this as your result. Okay? Now, step 3. Calculate skin friction drag of area A if the flow is laminar, which is this. This is a transition point, XTR. This is a flow laminar. So this is called DFA laminar. Okay. Step number 4. Of course, you can add them together, right? Because area A you have a laminar flow, area B you have a turbulent flow. So whatever the skin friction drag obtained here and here, you can add them together. So you can say dF is equal to dFA laminar plus dFB turbulent. Note, this is biplane. So, skin friction drag total is actually not the twice of it, this is 4 times dF. Because you have 4 surfaces. 1 wing, 2 wing, top, bottom, top, bottom. So total 4 surfaces. So you need to multiply by 4 to have a total skin friction drag. So this is the procedure to solve this problem. And then this is one of the homework assignments. So I really strongly recommend you to do it by yourself. This is the process. Okay. So let's move on to the next page. Okay. So the rest of this unit D2, we are going to remember what we did in N1 was mainly ideal flow. This is one of your project, which is flow of a circular cylinder. If the flow is ideal, there's no drag. Okay. But in reality, the real flow comes with the amount of drag associated with. This drag is purely viscous effects based drag. 2 things involved. One is because of the separation, you create the pressure difference. It's called, it's just one thing. One of the type of drag which I want to talk about was drag due to separation. We want to denote this one with dP. Okay. And this is called pressure drag. Number 2 is, of course, drag due to skin friction. This is called dF. This is called parasite drag. Okay, let's take a look at it once again. So those are the 2 things which we completely ignored on ideal flow process because we completely ignored the viscosity. So those 2 are called by viscous phenomena. Viscous phenomena creates 2 different kinds of drag. In this case, you have a flow separation. At the same time, even if the fluids stay attached on the surface, it comes with a drag because of the skin friction. Skin friction drag depends on if the flow is either turbulent or laminar. Okay. Same as here. This is the flow over ideal flow. Okay. If the flow is ideal, there is no boundary layer, so the flow gets in, hit the stagnation point, and then after that slide over the surface and depart from the surface. This is ideal flow. But because of the boundary layer, okay, the boundary layer, within the boundary layer, you have a velocity changing from 0 to free stream. Because of the boundary layer, you are going to develop skin friction drag, and also could be a separated drag if you have a high angle attack. Separated flow creates the stall. So next page. So flow separation happens, especially if you pitch up really high angle attack. Flow separates on the surface. The separation could occur at the leading edge or trailing edge depending on the thickness of your cross section. If the airfoil tends to be really thin, separation begins to occur at the leading edge. It's called leading edge stall. If the airfoil is thick, the separation usually occurs at the trailing edge and begins to increase. This is called trailing edge stall. But if the separation happens, separated flow gives you a pressure relief. In other words, if you plot for a pressure distribution, CP plot, okay, for the attached flow, this is the pressure distribution if the flow is separated. This is the pressure distribution if the flow is not separated. So, of course, because of the separation, you have a pressure relief. Okay. So, separation is caused by mainly dpdx, which is called pressure gradient. If the pressure gradient is too steep, the nature basically separate the flow to adjust the pressure gradient. So you're going to relieve some of the pressure because of the separation. Okay. If the flow is stay attached or flow is separated, it's going to make a huge difference. If the flow is attached, of course you have a more lift and less drag. But if the flow is separated, you have a less lift and more drag. So you need to understand the lift and drag is purely because of the pressure distribution on the top and bottom surface. Separated flow dramatically alter the pressure distribution on the surface. So prediction of a flow separation is pretty important. Again, a prediction is based on the boundary layer analysis. So the software X-Flyer 5 really combines potential flow plus boundary layer analysis so that it can predict the separation of the flow over the surface. If we can predict the flow separation on the surface, we can predict the stall. So obviously, for the angle of attack from low, medium to high, you can see the flow stay attached. You begin to have a separation line, then flow is completely separated. Of course, the lift value is going to be very, very different. If you have completely separated flow, you're going to reduce the lift and increase the drag quite a bit. So this is the case of a, as you can see, this is the trailing edge stall. So stall region begin to happen, then move forward, and then completely stall down. Okay. So this is the conclusion of viscous effects on drag. Okay. So as you really need to understand, you have two different components of a drag due to viscous effects. One is drag due to skin friction. This is called parasite drag. The other one is drag due to flow separation. This is called pressure drag. Okay. So if you compare flow over circular cylinder against flow over, let's say, airfoil, streamlined bond, the big difference here is major component of the drag of this case is mainly because the flow is massively separated here. So big portion of the drag is essentially pressure drag. You have a huge separation, creating huge drag due to separation. Now, this is a small minor component is skin friction. As long as flows stay attached, you do have a skin friction drag, but this is a massive separation, so most of the drag components comes from drag force due to flow separation, pressure drag. Now, this is cross-section of a wing called airfoil. Flow is almost all attached, and you have a separation region a little bit. So almost all the drag comes from skin friction here, at least when you are doing cruising condition. So somehow, if you want to minimize this skin friction drag, it's going to be a huge improvement. So that's where natural laminar flow this one comes in. So in other words, NACA 6 series airfoil is one of the design that you are going to reduce this pressure gradient. Usually, conventional airfoil, something like this. This is a really dpdx is, of course, favorable, but massively favorable. So you are going to really accelerate the flow, this one, you are going to reduce it. dpdx is really low. This is dpdx high. As a result, you are going to retain more laminar flow on the surface. This one is, so laminar flow region is extended. Now obviously, if you compare laminar and turbulent flow, skin friction drag is pretty different. Laminar flow comes with lower skin friction drag. So you can reduce this portion by choosing 6 series. So that is end up being a significant improvement of range, maximum range. So let's understand properly. The drag is composed of 2 things. One is due to separation, one is due to skin friction. Now, using streamlined body over the body like this is going to massively reduce the pressure drag. Then if you carefully design wing cross-section called airfoil, you can further reduce the skin friction drag. So that is the design of airplane. Design of airplane begins from 2D understanding of what is causing the drag. Okay. So this is just a very brief introduction to Aerodynamics 2. Aerodynamics 2 covers a lot more in depth on viscous flow. Okay. So let's stop.